And that, that'll be more dramatic when we go to rotation group in 3 dimension, and especially when we go to, that what will happen there is I'll be able to rotate what I know how to do, which is I take vectors and write 3-dimensional Euler angles or whatever they taught you in some or other course. We know what it means. There's a planet Earth, it turns this way, and we do that, right? So we have very good intuition. Then we'll show you that if you multiply 2 by 2 complex special unitary matrices, it's the same group. And that's totally mind-boggling. Not only that, it's actually the world is built from that group and not as of 3. So the actual basic building block is 2-dimensional. And, you might not believe me, but it's really that, and it's very basic. So people who do computer games know that, because if you understand this, rotations using quaternions are much faster than rotations using 3 by 3 matrices if you do computer games. And that's what it is. They work in the 2-dimensional complex space, and that's much more natural. So, so it gets to be surprising. I mean, you find mathematics, and that's what's nice about, mathematical language in natural sciences. If you're lucky, it leads you someplace which makes no sense to you at all, because you have no intuition on, complex 2 vectors. But it's the right thing. Nature chose that, even though you're too stupid to think that way. You don't have neurons that rotate, complex 2 by 2 numbers in your head, but that's the right thing.
So I guess then, at that point, then it would be reducible because it's down to its 2 by 2 movements, I guess.
Yeah, there is, it has to do with this year's Nobel Prize and Roger Penrose in Physics Nobel Prize. But, there are people who think we have quantum structure. How do we put the space together? So lots of people come to your point of view, says, this is the smallest block that we have. And from that, you can produce other irreducible representation by putting it together, and that's called spins. So it goes from spin 1/2. Spin 1 is our usual vector, but then there are, things like quadrupoles which have more complicated spins, so they're called spin, 3, 5, 7. But then there's this even spin, which are very hard to understand. They're constructed from this guy. And yes, nature uses this all the time, this little spin. So this is this fundamental block, but irreducible representation, there are always infinitely many for continuous groups. For finite groups, you cannot have more than you have classes. So that's easy to understand. Just when you have 7 Fourier modes, 7 sites on a lattice, you cannot have more than 7 Fourier modes because matrices are 7 by 7, so you can have more irreducible representations than what you have. But because continuous groups are infinite, you find you can construct more and more complicated objects. And you know this in Fourier modes. In continuous Fourier analysis, you can have as many Fourier modes as you want because there are infinitely many of them. But you're right. It's not what we call irreducible. It is one irreducible representation. It's the smallest one, but then there is, many other irreducible representations which are built from these guys.
That's how. From, yes, the same group, there would be a separate irreducible representation.
Yeah, there are infinitely many. And for rotations, you understand it very quickly. The moment you understand that there is a 2-dimensional complex and 3-dimensional real, then you realize, there'll be infinitely many because there'll be a 4-dimensional complex and, 5-dimensional real. So in quantum mechanics courses that teach you, because that's all we see in atomic and nuclear physics, we see these high representations. All the spectroscopy, all the colors of the light, they're labeled by irreducible representations. So the reason why, when we look at a star and we see spectral lines, they are irreducible representation. Every place, if we look in the universe, same law applies, same irreducible representation. So they, that's all we know about. Well, all chemistry, all material science, all astrophysics, everything is built on irreducible representations because they inherited from quantum mechanics in that case. If you don't care about quantum mechanics, then here are examples of irreducible representations. You look at the sun, it's a sphere. I mean, if you look very closely, it has turbulence on it, but it's a very good sphere. It's a heavy object and it's slightly deformed because it rotates. It's a good sphere. It's elastic. So you can do what's called helioseismography. If you were able to hit the sun, it would ring, but it would ring not in Fourier modes on a circle, but in the Fourier modes of a sphere, which are called spherical harmonics. They're called harmonics because, they're harmonic motion like the harmonic for the circle. So there's no quantum mechanics in this, but you look carefully at sun and you can see thousands of eigenfrequencies, very sharp. So this huge sphere is oscillating in lots of eigenmodes. Now, why do you care? You don't know what's inside the sun, but by understanding the oscillating modes, you get information on the composition of the whole object. And it's all classical, it's all 19th century mathematics. But today you can measure it so carefully because, you can measure redshift on the surface of the sun, every place, average it. And you can measure the oscillations of this thing, not just one, but thousands. It rings like a bell. It's totally amazing. It's a whole subject called, and it's classical. But it's irreducible representation of rotation group in 3 dimensions. And it goes on, the way you measure gravitational waves, you have to measure frequencies very well. You measure them by having a sapphire ball. So you have, a very perfect spherical ball of sapphire polished to optical precision, which has the Q factor, oscillation factor, which is 10 to the minus 11, means when you hit it, it'll oscillate 10 to the 11 times before its amplitude falls by factor 2. So this thing rings extremely well, but what you're measuring are irreducible representations of rotation group when you say that. And you use that very high frequency to be able to measure very small shifts caused by gravitational waves as they cross Earth, and you're measuring apparatus, and they deform the apparatus. In physics, angstrom is the size of atom, roughly speaking. Fermi is the size of nucleus, so it's much smaller. And these oscillation bend rods, which are, meters long, that bends them 1,000 of a Fermi. So you wouldn't think you can measure something that's 1,000 of the Fermi. But because you express it in terms of these Fourier modes, you can, even though just like on a piece of wire, you don't understand atomic structure, but you get extremely good measurement of the oscillation of the object. And you can do this on, again, if you didn't know group theory, you don't have to call it group theory. You can call it spherical harmonics or whatever, quadrupoles, octopoles, whatever you want to call them. You could not make this. You could not make good trains. You cannot make good planes. You can't make good anything if you don't understand the eigenmodes or irreducible representation. It's very, very often, for example, in materials, if you take a piece of aluminum and you bend it a little bit, it's extremely elastic, and it's very in audible frequency, it absorbs very little sound, converts it into heat. It's really good. But if you bend it too much, you start damaging it, and that turns the nonlinear terms become important in the bending. So you care about not just the planes, but the curvature, etc. So lots of stuff, you always have to understand elasticity first, meaning how it responds linearly. In other words, there are matrices. These matrices can be decomposed in irreducible representations, and that's how you understand the response. Otherwise, you wouldn't be able to do anything. Now, I'm giving you a kind of very bird's eye view of why this works. And in engineering, they just teach you this is what you do. I think that's old fashioned because engineers also have to do new stuff. It's not like, you're trained and nothing will change until you die. You're trained and 3 years later, all technology will change. And if you don't understand, why it works, you can't possibly do good work in that situation. So I really think there is, not much difference between physics and engineering when it comes to, really pushing the envelope, developing new stuff. They're indistinguishable. For example, gravitational wave experiments are amazing engineering, because you have to make devices, mechanical devices like the sapphire, perfect sapphire balls, which are, good not 1 part in million, but, 1 part in quadrillion. And if you don't do it, then you're a third world country. You just can't do it. It's like, it's not optional. Somebody's going to do it.